Hi guys, so we are going to be talking about sound, the second half of notes, specifically harmonics. So when we were talking about sound previously, we were talking about things in terms of intensity, volume, resonance. Now we're going to talk about the specific harmonics, and that is really related towards music. So just as a quick review, so remember that wave interference is a superposition of waves, meaning that we have two or more waves that are existing at the same place at the same time, and they're interacting. Okay, so that interference is an interaction. They can help each other or they could hurt each other, but they're interacting. So when the medium, because we're talking about sound, so it needs a medium to go through, but when the medium has more than one wave going around, then we're talking about a displacement that's the sum of those two. If you have one being negative and one being positive, we're still adding them together, but it can be causing a cancellation. So we have constructive interference. So this is when they add together, they're helping each other. They get bigger, as you just saw that text happen. Those of you who had me in class know that I like to say that they're on the same team. So if we think about it like sports, right? They're on the same team. So that is helpful when you're going to help the other person. Okay. Same team is same side of the line. So if you notice, both of these waves are on the top. So same side of the line, they're on the same team. They're going to help each other out. So they're going to add together. If you notice, there's just kind of a ghosting of each one of the two when they're overlapping. So you can see that this little one comes all the way through, and the big one right here comes all the way through. So they're not bouncing off of each other. They just happen to add while they're on top of each other, but they continue to do what they were doing afterwards. The other type would be destructive. So they are not adding together, they would be taking away. They would be canceling. Okay, they'd be getting smaller, as you just saw the text go. So if constructive is same side, same team, then destructive would be opposite teams or opposite sides of the line. So you see we have one on the top, one on the bottom. Okay, and when they happen to overlap, they're actually going to cancel each other out. Now that cancellation is only because these two waves happen to be the same size. If they were different sizes, you would have some left over. If the top one was bigger, then you'd have some left over on the top. If the bottom one was bigger, you'd have some left over on the bottom. But either way, it is getting smaller. So there's a special type of wave interference, and that's called a standing wave. So remember, to make a standing wave, you need exactly two waves. No less, no more. Those two waves have to be traveling in the opposite direction. They have to be the same height or the same equal magnitudes. Okay? They have to be the same frequency. So many waves per second. They have to be the same wavelength. So overall, they are the exact same wave, but they just move in opposite directions. So when we do that, you see these two waves are the exact same. One is going to the right, one is going to the left, and what we get is this blue line where there is an oscillation happening, but it doesn't look like it's moving left and right. That's a standing wave. The nodes are the part of zero displacement. The antinodes are the parts of maximum displacement. So if I'm going to label these, the node would be this dot. It's not moving. The antinode would be this dot, that movement piece. So for your harmonics, most of these I have drawn in for you. Okay, but the fundamental or the first harmonic, you need to know how to call them by both the fundamental or the first harmonic, either one. For strings, we are in strings right now, would look like just one bubble. Now, if you remember, if you were to take a snapshot right here at the top, right, one wave is an up and a down. So this, if I was to fill this in, would only be 1/2 of a full wave. So the length of that string is one loop, or lambda over 2, the wavelength cut in half. Okay, so for the next harmonics, one thing that we have changed from years past is we no longer talk about overtones. We only talk about harmonics. So the second harmonic, if the first harmonic was one loop, second harmonic is going to be 2. There we go. And if you freeze it at either the top or the bottom, you see we have both an up and a down, making one full wave. So if we do second harmonic times lambda over 2, we get 2 times lambda over 2, which cancels out to being just lambda, or one full wave. All right, keep going. Third harmonic has how many bubbles? Yep, 3. So the number of loops that are always going to be listed on your picture for strings is going to be the number of the harmonic. So the length is going to be 3 times lambda over 2, which does not reduce down. So let's try the fourth harmonic. Fourth harmonic would be how many bubbles? Right, 4. So we do the harmonic number 4 times the first harmonic's lambda over 2. 4 lambda over 2 gives us 2. And you can see that really clearly here. You have one wave ending here. Then you have your second wave ending at the end. All right, that's it for strings. So if you remember in your notes, so for continuing on, you're going to count the number of loops. Okay, each loop is half of a wave. All right, for pipes. So pipes are a little different. What's happening is inside of a pipe is air. And that air is the piece that's actually vibrating. So commonly right here in the organs, okay, the air is what's bubbling rather than a string like a piano or a violin. Okay. And that air vibrating is what's giving us the sound. Now, pipes, first harmonic. If you see here, we have an antinode on either end. We have a node in the center, so they look a little weird. Okay. If you look at a full wave, okay, and then you look at it, it's starting here, ending here. Right? Well, if I kind of do this and truncate it, we have 1/4, 1/4, 1/4, and 1/4. So if we're starting from the first fourth to the third fourth, what we have is 2/4 or half of the wave. So open pipes are the exact same as strings, meaning that the length of that pipe is also a lambda over 2. Okay. Second harmonic, if you notice the first harmonic has one node, second harmonic is going to have 2 nodes. 1, 2. 2 lambda over 2 gives us 1. One full wave in there. So third harmonic would give us 3 nodes. 1, 2, 3. 3 lambda over 2. Okay, what you should notice is that what is always at the end of the pipe? Right, an antinode. The reason is if I have a pipe, right, and I draw my wave like normal, well, if you notice, what's happening right here to all the sound? Right, they're canceling. So if they cancel, will any sound come out? No, not at all. So that's why you've noticed that things have shifted down. So instead of starting the pipe here, we would start the pipe here, where there's an antinode, and add this little section to the end. Extend the pipe. We still have one wave, but this time sound would actually come out of the pipe. So that's why we always need to start an open pipe with an antinode, because nodes would cancel it out. All right, that finishes us up for open pipes. Now let's move over to closed pipes, which is our special circumstance. So closed pipe. So that is a pipe where 1/2 of the wave has been blocked off. So, or half the pipe, sorry. So right here is closed. This is closed. Nothing's coming in or out. Okay. What you notice is if I again draw my full wave up here, we are going from the first node to the first antinode, which is right there. That is what this picture is. So that's 1/4 of a wave. So a string is going to be 1/2 of a wave. An open pipe is going to be 1/2 of a wave. A closed pipe is going to be 1/4 of a wave. So third harmonic, we have 3 pieces of our wave here. We have 3/4, so we have 1, 2, 3. So we would have 3 lambda over 4. The next harmonic is the 5th. So we would have 1, 2, 3, 4, 5/4. Now, did you notice I skipped 2? Right, the 2nd and the 4th harmonics I skipped over. Why? Well, for a normal closed pipe, I just turned it this way for simplicity when I'm drawing, ends in an antinode. Ends in an antinode. If I had a 2nd harmonic, I would have 2/4, right? So I'd have 1, 2. So I would end my pipe here for the 2nd harmonic. Well, what do you notice? I'll do this for the opening piece. What do you notice is on this end? Right. Evens. Sorry about that. That is really hard to see over there. Evens end in nodes. So even harmonics end with a node. Ending with a node means that there would be no sound coming out. So they can't exist. So to recap, so overall recap, a string is going to go normal harmonics 1, 2, 3, 4, 5, and so forth. The length is properties of lambda over 2. So the third harmonic would be 3 times a lambda over 2. A open pipe is going to work the same as a string. So the length is proportional to lambda over 2. The closed pipe is going to be proportional to lambda over 4. And there are no even harmonics. So if I ask you what the first 3 harmonics are for strings, open piped, and closed piped, for both strings and open pipe, you would say 1, 2, 3. For closed pipes, you would say 1, 3, 5. All right, guys, I hope this helps. Look out for the video on examples as well, or go back and watch the first sound video for all the other notes. Thanks, guys. See you in class.